Good afternoon, and I would like to thank our friend Emilio and Gianmaria for his nice words, and thank you all the organizers for having invited me to talk about yeast derivatives. This is my very passion. I would like to explain the production techniques and all details that are important, and I will focus on the enological characteristics of these products. I will start with the more academic topic, and we will distinguish into 5 types of derivatives. That is yeast hulls, inactivated yeast, yeast autolysates, and we'll focus on them. And then there are also protein extracts and a last product. There's 3 types of products. Sometimes considered to be basically the same, that is, that can be used at the same time, but OIV for hulls attributes importance to, well, all the three of them are derived from Saccharomyces, and the cell wall is very important because the preparation method must be in line with the surface area and absorption capacity, because they need to fix those molecules that are detrimental to yeast. As such, hulls are compounds and they have a high level of insolubility. Insolubility in water must be less than 10%, and the polysaccharide fraction must be preserved. So they need to have a certain amount of carbohydrates, and 60% of them should be glucans and mannans. So autolysis should be really reduced. Native or inactivated yeasts, according to the OIV, could have started autolysis thanks to endogenous enzymes that are typical of the yeast and that can work optimally through variations in temperature or in pH. As such, derivatives are more soluble. I mean, those inactivated yeast are more soluble than hulls, up to 40%, and OIV also attributes importance to free amino acids that could reach up to 10% of the dry substance. And this is so because inactivated yeast, even if they, it is important for them to consider the nutrients for yeast during dehydration and alcoholic fermentation. Well, if we want to, we can obtain lysates that are products of autolysis associated to thermal treatments. They're very soluble in water. The soluble part goes up to 80%, and they have a quantity of free amino acids which is higher, up to 40% of dry substance, and this is the typical nutrients for yeast in alcoholic fermentation and rehydration. So these products have a different identity, they have different features. OIV for each of them sets forth some criteria and recommendation with regard to the limit of potentially contaminants such as heavy metals, and there is a maximum amount of vital yeast and contaminated contaminants. The European legislation also sets forth different characteristics and applications. For inactivated yeast, there is no constraints at any level, whereas you have yeast hulls that can be used at any time of winemaking, up to 40 grams hectoliters, and for autolysates you have some application limits in terms of when they can be used, not on the finished product. If we set aside the yeast hulls that undergo a very minimum process, when we query about autolysates and inactivated yeast, there are various technologies, various methods that are used. How do we obtain those yeast derivatives? You start from a yeast that is multiplied in aerobiosis, for instance, in the bead, and at the end this mass is undergoing autolysis, after which they are dehydrated with various methods in order to obtain the commercial powders. In order to reduce autolysis, there are 4 techniques that are available. 2 of them prevail when it comes to obtaining derivatives for food. Sometimes you produce an osmotic shock on the cell, and these 2 methods are less used. For autolysis, you have the activation of endogenous enzymes in order to promote cell lysis, whereas thermolysis is a thermal shock that is used in order to make the yeast inactivated according to parameters set by OIV, which also induces a certain cell lysis. By treating the yeast thermally, you can increase the level of proteins and other substances. Here you can see what we've just described. I've underscored certain boxes and I've put them in red. In these cases, temperature is very important. For autolysis, temperature is very important because if we follow this path, we want to obtain the optimal criteria for endogenous yeast. If we use the thermolysis path, or if we want to obtain microbial inactivation, we have to increase temperature. There is this first phase of thermal treatment for these products, and then you have the phase in which you dry powder. Even if you work in a vacuum, you need to have a certain amount of thermal stress for a product. So why am I mentioning temperature? Because according to our experience and according to biography as well, temperature induces certain changes that are important in the composition of these yeast derivatives. When it comes to composition, what are the most important components in enological terms? Well, there are many of them because derivatives are extremely complex. I would like to mention them all without going too much into details. I will start with colloidal substances, then I will talk about the insoluble residue, which is important in quantitative terms, especially for inactivated yeasts and hulls, the lipidic fraction, the amino acids, the aromatic components, and certain reducing compounds. We'll see what are the characteristics that these substances convey to our products and how winemaking methods can have an impact on all those components. Let's start with colloidal substances. These are proteins, glycoproteins. We can see them in those 2 images. First of all, what levels of concentration can we find? If we talk about proteins, some tens milligrams per gram. For colloids, total colloids, contents can be 50 up to 250 milligram per gram of commercial powder. What is the impact of technology on those 2 fractions? By increasing process temperature, you get a decrease of protein contents. For polysaccharides, you know, the nanoproteins are stable proteins and they're less affected by the thermal treatment. So in this case, there is not such a considerable impact. And now let's look at the insoluble residue. This is very important because you reduce fatty acids, and we can see that the 5 commercial derivatives can reduce the content of octanoic and decanoic acids. Why some products are more effective and some are less in terms of reduction? Well, D4 and D8 are very active and they feature a higher content of insoluble fraction. D1 and D3 are autolysate, whereas D3 and D4 and D8 are yeast hulls, but esters are also reduced. Here you can see the effect of the ethyl decanoate, which is very important for its fruity aromas. You can see that D4 is the one that leads to the most pronounced reduction. For these compounds, the lipidic content of the soluble part is very important, and you can see that there are many lipids in D4. This is why those compounds are retained. Beware of addition in large quantities and in a late phase of those products that have many lipids and a high soluble content. Let's see what happens here. You can see that the 2 derivatives, well, this is the fermentation speed. The 2 derivatives in blue can increase fermentation speed, and the process can be completed 2 days in advance vis-a-vis the red curves. What is the difference here? The difference is that the blue derivatives contain many more amino acids, a higher content of amino acids. In this case as well, the process temperature has a very important effect on amino acids, because at high temperatures these are degraded and there is the Maillol reduction, a reaction with sugars, with carbohydrates. Here we have 3 derivatives that are obtained mechanically, M2, M3, M4, and then we have a thermolysate. The numbers that you can see in blue and in red are a maximum process temperature. Obtaining products with lower process temperatures enables us to have less amino acids and therefore a wider application in the food sector. The aromatic component is the most complex element that we can find in terms of yeast derivatives composition, because derivatives have a very complex interaction with the wine aroma. They can fix other molecules on the insoluble fraction. They can remove off flavors, but they have their own aromas that can be released by powders. Moreover, on some conditions, they can increase the volatility of some esters. Let's have a look at all those effects one by one. Interaction with the insoluble component. Here we have 2 different derivatives, one that is mechanic and the other obtained thermally, and 2 of the most important fermentation esters, ethyl azanoate and ethyl acetate. You can see that in both cases you have a reduction, but you can see that the one that has been obtained thermally with higher process temperatures leads to a more pronounced reduction. Derivatives also have their own aromatic component. What is it made of? First of all, some aroma that derive from the yeast metabolism, some that derive from a Maillard reaction involving acids and fats, and then there are some others that come from the lipid oxidation. All those substances can be transmitted to wine. Well, enzymatic lysates are more rich in terms of Maillard components because of more amino acids and precursors. Thermolysates tend to have more compounds coming from lipid oxidation, And in mechanic lysates, there is a higher concentration of aromas that come from the yeast metabolism, alcohols and esters. These substances can be released into wine. Here you can see some examples of different doses. Here you also have a yeast extract, and you can see how these compounds can be released. It depends upon the type of the product, its solubility, the dose. The higher it is, the easier it is to get this release, and contact times. There is an investigation by Professor Pozo Bayon, made in Spain, that demonstrates this. We've also noticed that oftentimes thermolysates, despite, and this is somehow a paradox, despite the fact that they have an aromatic component of powders that is the least representative vis-à-vis the other products, mechanic and enzymatic, they are often distinguishable when they're added to wine. And here we have considered three different ones, a mechanical, a thermical, and enzymatic, and they were added to white wine. We asked, well, the dosage is very low, but we asked the panelists in which of those samples they could perceive more the abstract yeast derivative. You can see that T, the thermolysate, is the one that is the most different. So what did we notice? That there is a 2-decanone, a compound that was the most concentrated, and it comes from lipid oxidation, and that is more concentrated in the tea sample, and that can also be found in wine. You can see that there is a higher concentration for thermally processed wine. This means that probably the relationship that ties the product and the wine follows this path. In some cases, you have an increase of ester volatility of wine at low dosages. It is more likely, and at temperatures that are higher. This means that this perception is something that we have, and we have a retroolfactory complexity that is more pronounced. In order to defend those thermolysates, I would like to say that this feature, well, there's something positive here, because this is a feature that you can find more in thermolysates, because they have less proteins that tend to tie the aromatic component, and I'm referring to soluble protein components. I would like to conclude by talking about some reducing compounds, because the yeast derivatives have a thiol element that is linked to the reducing feature. And here there is two different lysate, one that is obtained mechanically and the other that is obtained thermally. And here you can see the maximum process temperature in the two cases. You can see how, if you consider the thiol groups that are linked to pellet, and those that are soluble substances that are characterized by soluble compounds, the mechanical autolysis enables us to have higher quantities of these substances than the mechanically obtained compound. That means that when we add to our end product to wine, over time, over months, here you can see the evolution up to 4 months, this wine will be more protected by browning. In red, you can see that after 4 months, there is no significant difference between the two products. I would like to conclude my presentation by saying that yeast derivatives are a useful tool. It is not the only one, but it is a useful tool that can be, however, more complex than we expected in the past. I think that it is necessary to enhance their application technique. It has already started. We should have the same evolution that we had for tannins. My dissertation was about tannins at the time, and I'm referring to the year 99. At that time, the botanical source of tannins was starting to be mentioned. Now we know very well what are the characteristics of the various tannins. In this evolution, we should consider the composition characteristics, dosages, and the ideal application time. And other features that are typical, is it a hull, is it a autolysate, what do they produce? And the production technique is key in all this. In some cases, it could be useful to promote those technologies that enable a reduction in process temperatures. In some other cases, that could be not that important, but in some it is. I would like to thank all the people who've collaborated. Many of these people are present here. I've seen them today, and I would like to thank them publicly for their enthusiasm and their